Okay, so we have looked at the least upper bound property. We've looked at ordered sets and an order on a set. The next thing we have to look at in order to prepare ourselves to construct a set of real numbers is fields. Now, we've already looked at groups a little bit. So we've done some abstract algebra already because we looked at groups when we first started looking at elliptic curves, and there is a group structure on elliptic curves, if you remember that. So now, before we can define the real numbers, we need to define what a field is. So just quickly to remind us what a group is. A group is a set with one binary operation, which you usually call it plus, which has closure under that operation, under the plus. It is associative. It has an identity element. And every element has an inverse, meaning that 5 plus minus 5 equals 0. Right, so that's the inverse of that. And then a group can be commutative, but it doesn't have to be. So a ring adds an additional binary operation to the set. So rings have two operations, which are usually called plus and addition and multiplication. And a ring is sort of an intermediate. It's not as much structure as a field, but it just adds the multiplication in the sort of the least way possible. So in addition, so a ring is a set that has a group structure, and in addition to that, it has a second operation, which again, of course, is closed under multiplication as well, and multiplication is associative, and it has an identity element. But a ring does not have to have an inverse for every element, and it does not have to have multiplication does not have to be commutative, although the addition does have to be commutative, but the multiplication does not. Then, so for a field, in addition to the ring structure, we complete the structure by saying that every element has an inverse, and also that multiplication is commutative. So it's basically two group structures. It's a commutative group over addition and a commutative group over multiplication. Then in addition to that, there's more structure between them because the identity has to be something other than the additive identity. So there's going to be one identity for the multiplication, one identity for the addition. So that's what fields are. So we're going to go over the field axioms. Oh, well, and then in addition to that, the field is distributive. Multiplication is distributive over addition. And we're not really going to go into any detail about all the cool stuff about abstract algebra, but I just need to show you what fields are, because what we're constructing is a field that has the least upper bound property. As you'll see, the rational numbers are a field, but they don't have the least upper bound property, and as a consequence, I've said several times, when you're trying to solve this, you can't solve that with rational numbers. So we're trying to make a field that will allow that to be true. So, okay. So what we're going to do with this video is I'm going to show you the axioms more formally, and then we'll look at the consequences of these, because there are a whole lot of properties of fields that are not actually a part of the definition. And then we'll look at an ordered field, and then we'll be ready to look at real numbers. So there are three sets of axioms for fields. There's the additive, which we usually call plus, but it doesn't have to be because they're abstract. So you can make a field that has any operation you want. And then in the Walter Rudin book, he numbers them like this. So if x is an element of f and y is an element of f, x plus y is an element of f. That's closure. A2 is commutativity, so x plus y equals y plus x for all fx, or for all x comma y. That's commutativity. Associativity is that x plus y plus z, quantity plus z, equals x plus quantity y plus z. That is associativity. And the last two, what's left? F contains an element 0, such that 0 plus x equals x for every x in f. That's identity. And 5, to every x in f corresponds an element minus x in f such that x plus minus x equals 0. That's the inverse. Now, one really interesting thing about this, so we're about to do the same thing for multiplication. One really interesting thing is that, of course, all we're doing here is describing the numbers that we already know. We learned all of this in grade school, right? That if you have 1 plus 2 in parentheses plus 3, that equals 1 plus parentheses 2 plus 3. But what these axioms are is that these are the properties of a field that are necessary in order for it to be a field. So what we're going to do as soon as we finish listing the axioms is we're going to look at some properties that you can conclude from these. One of the really interesting things is how minimal these elements are. These things must be here, but there's a lot of other stuff that we think about when we think about numbers that actually are not one of the axioms of a field because they can be derived from these axioms. So for instance, this says that f contains an element such that 0 plus x equals x. And something that's not here is that there's only one 0. There are not two elements that this is true. If you see like y plus x equals x, then y has to be 0. So that's something that we're going to be able to derive from these axioms. It's interesting how minimal the axioms are. So this is the additive properties. Next up is the multiplicative properties, which are the same thing for multiplication, basically. So we call this M. So M1 is closure. So again, if x and y are both in F, then xy is an element of F. xy equals yx for all x and y in F. This is commutativity. So commutativity is required for a field. It's not necessarily required for a group or a ring. It's closure. M3 is associativity again. xy times z equals x times y z. M4 is that F contains an element 1, which is not the same as 0. So they have to be different elements such that 1 x equals x for every x. And then M5 is that if x is an element of F and x does not equal 0, then there exists an element the inverse of x element of F such that x times the inverse equals 1. So you can see right here, it's very interesting. It's not just two operations, multiplication and addition. In addition, there's a relationship between the two. Multiplication is not quite the same as addition because you can't divide by 0. That's what this little thing right here is. You can always subtract by, there's nothing that you can't subtract by. You can subtract any two numbers, but you can't divide by 0. That makes the multiplication slightly different, and it sort of it intertwines the two operations in a way that adds a lot more structure than just having the two. And that's also why 1 does not equal 0 is also related to that. Finally, there is there's a distribution rule, the distributive law. Which is x plus z equals xy plus xz. Again, that also clearly, obviously, connects the multiplication and the addition, right? I think we might get into abstract algebra more later, because I love it, but it's not really necessary for what we're doing right now, which is just building the real numbers so we can get to the complex numbers so that we can connect the complex numbers to elliptic curves. So a couple of remarks. We use the usual notations for these, and I think it's interesting that you have to say this because it emphasizes to me that all of this is abstract. It doesn't have to be, but the fact that, for instance, division, we can say x divided by y, or we can say x divided by y this way, or we can say x times the inverse of y, that these all mean the same thing. We have to actually say that because we're defining something from scratch. The fact that all of this mirrors what we know from regular math is, in a way, I mean, of course it's not really, but in a way it's a coincidence because we don't have to be talking about real numbers. There are other things we can be talking about, other ways you can make fields instead. So pointing out that these things all mean division, for instance, kind of emphasizes that. Another thing to observe is that Q is a field, as I just said, because all of this is clearly true of rational numbers, right? That's obvious. We know that rational numbers are commutative, they're associative, they all have inverses and so on. So Q is obviously a field. As I said, the integers are not a field. Real numbers are also a field, but again, what we're looking at is what's the difference between real numbers and rational numbers. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.